Colleagues, it's my great pleasure to welcome you to this first ProEC event in 2021. This is the second talk we have in this online format after the first such talk of Professor Leibold-Gut in October 2020. I'm sure many of you still remember that. The speaker of today is Dr. Andrea Fortier of the University of Bern. I would like to thank her very much for accepting our invitation to give this presentation today. Dr. Andrea Fortier is the instrument scientist of the Keop satellite, where CHEOPS stands for Characterizing ExOplanet Satellite. However, the CH can also be interpreted as being standing for Switzerland, and the reason for that is that the CHEOPS project is a joint mission of ESA and Switzerland. It's led by the University of Bern in collaboration with the University of Geneva. There are, of course, also many more partners, and Professor Willy Benz, who is the principal investigator of CHEOPS, therefore sometimes says that CHEOPS might be a small, S stands for small class mission, but with a project organization and a complexity like a big one. But in any case, I'm sure we will hear more about that from Dr. Andrea Fortier in a short time. But let me first also go through her CV. So Andrea Fortier got her PhD in astronomy on the theory of giant planet formation at the University of La Plata in Argentina, where she later also worked as a postdoctoral fellow. But already in 2010, she came as a postdoc to the University of Bern, where she was, however, working still on the theory of planet formation and evolution. But then since 2013, she became the CHEOPS instrument scientist and a member of the CHEOPS science team. And as the CHEOPS instrument scientist, she's coordinating the work of several science team working groups. She was in charge of the coordination and the planning of the in-orbit commission of CHEOPS, which has occurred in the last year. And now, with CHEOPS observing, she is in charge of monitoring and characterizing the CHEOPS instrument performance. So this is a lot of very important tasks that she's doing for this mission, and we will hear about that during her talk. Before we start, I unfortunately also have to share some sad news tonight. Professor Dr. Hans Balsiger died in hospital yesterday. I'm sure that many of you knew him. Hans Balsiger was not only the director of the Physics Institute in Bern and the professor of experimental physics, he was also, among many other things, the principal investigator of the ion mass spectrometer on Giotto, and he was the original hardware PI of the Rosina instrument and Rosetta. And these, of course, were extremely important space missions. But I'm also mentioning that because of an additional point, which is important today. At the time, Hans Balsiger was also very important in bringing Willy Benz, the PI of CHEOPS, to Bern as a professor. So in this sense, it's also thanks to Hans Balsiger that we can listen to this CHEOPS talk today. This is, of course, a very sad loss, and I'm sure he will be missed by many. But I'm also sure that if Hans Balsiger would know, he would be very pleased that today we can talk about CHEOPS as such a great new space research to which indirectly he also contributed. Let me make another quick note before we start. At the ProEC committee, we are, of course, aware that such an online setup as we have today cannot fully replace our usual normal ProEC events in person. This is in particular true regarding the fact that usually we have the direct informal exchange with the speaker during our aperos, and at the moment the apero part is of course not possible. We don't have any choice regarding that. But we, of course, hope all very much that sometimes in 2021, maybe in the summer, we will see we can go back to the normal setup that we all like so much. I hope that despite this limitation, you will nevertheless find our event tonight stimulating for the fascination of space that we all share. Finally, a small last comment on the practical side. There is, of course, still the possibility to ask questions. And for that, please either type your question into the Zoom chat or use the raise hand feature in Zoom. So we will then go through your questions once the talk is over. And with that, I would again like to thank Dr. Andrea Fortier very much for the talk. And so the floor is yours. Please, Andrea.
Thank you. Thank you. I will then screen. Okay, so you can see my slides.
Yes.
I hope yes, because I cannot hear you. Thank you. So thank you, Christoph, and thank you to the ESA Institute for inviting me to give you this talk about CHEOPS, the Characterizing ExoPlanet Satellite. But before talking about CHEOPS, let's start where everything started, that is with the discovery of the first extrasolar planet. So as you well know, in 1995, the first exoplanet was discovered by two Swiss astronomers based in Geneva, Michel Mayor and Didier Queloz, who in 2019 received the Nobel Prize in Physics. The planet in question is 1 Pegasi b, and there was really a surprise to discover a planet like this because it's from what we know from the solar system planet. Half the mass of Jupiter, and it's very close to its star, that is a solar-like star, in 4 days. So this really changed everything we knew about planet formation. And just to have an idea, let's see what was knowledge before 1995. So we only have new confirmed planets of the solar system because Pluto was still a planet by then. Then there was a reclassification later on where it was downgraded to a dwarf planet. And now we are 8 planets in the solar system. We knew one inhabited planet, that's the Earth. It's still the only one we know that hosts life. And just the idea of numbers, these are not all, the only numbers one can make, but the closest planet to the sun is Mercury, that orbits around the sun in 88 days. And the farthest at the time was Pluto, that does the same in around 250 years. So what is current knowledge? Well, we know 1,400 exoplanets that are confirmed and around 700 of multi-planet systems. So around 700 of systems with more than one planet orbiting around the host star. Although we still don't know if any of these planets host life, we know that there are around 20 that are in what we call the habitable zone, that is where water can be sustained in liquid form, and that these planets are probably of rocky composition. Therefore, they can, in principle, host life. And just to go to the extreme, the closest planet to the star known so far goes around its stars in only 4.3 hours, and the farthest in 1 million years. So, as you can see, it's not a minor thing to say that this discovery 25 years ago revolutionized our sciences, because now the space is so wide and we have to accommodate so many things and to explain the formation of planetary systems that goes through this diversity. But the first question is, how are exoplanets detected? And the immediate answer by most of the people would be, well, we can see them, we can take a picture of them, we can have a direct imaging of the planet. This is true, we can detect exoplanets through direct imaging, but it's very difficult. And it's very difficult because the star is very bright and it outshines completely the planet. It's like trying to detect a firefly standing by a lighthouse. To have such a precise machine to be able to detect the light from the firefly that it's basically almost impossible. Unless you can, of course, block the light from the star. And that is done with coronagraphs. As in the picture that we see here, we cannot see the star that is in the center because it's blocked by a coronagraph. And therefore, we can see these points here that are planets. But also here you have the scale. So this size represents 20 astronomical units, and 20 astronomical units is the distance between the sun. And so these planets are very far away from the star. We cannot detect something like, for example, the Earth around a star like the sun. Usually then this technique works for planets that are very far away. There are some exceptions, like the figure that you see here with this little light moving around. Here the star is also hidden by a coronagraph, and this planet is only at 9 astronomical units from the star, basically the same as Saturn from the sun, and it's going in a circular orbit. So you see it projected on the plane, but this is orbiting around the star, and it's now passing probably behind the star. So with this technique, around 140 planets have been discovered so far. But I mentioned that we know more than 4,000. So where are these detections coming from? These detections are coming from what we call indirect detections. So we don't see the planets, but we see something happening on the star. And the indirect detections come in different flavors. There are two that are the most common ones to actually detect extrasolar planets. And the first one I'm going to mention is the radial velocity method. And I mentioned this first because it's the method that was actually used to detect the first planet, the 51. And also it was the leading method at the very beginning of the detection of extrasolar planets. So what's the idea? Well, we observe a star, and if the star happens to have a companion, then this companion, by gravity, is pulling the star. So basically, physics is that the two bodies are moving around their common center of mass. Or in other words, the star cannot stand still in the same position. It feels the attraction of the companion and it moves. And how can we detect this movement? Well, we can obtain the spectra of the star, meaning that we basically take the light from the star, we put it through a prism, we see all the wavelengths, and there we see lines, what we call absorption lines, that these are lines from different molecules that are present in the atmosphere of the star and that absorb certain photons in certain wavelengths. And it turns out that if the star was standing, all the lines are always at the same position. I know where the lines are because I can measure that in the lab. But as the star is not standing still, the lines move. They move around. And when the star is coming toward me, shifted towards the blue region of the spectrum. And when the star is moving away from me, are shifted toward the red part of the spectrum. This is called the Doppler effect. And by measuring how much these lines move, I can know what is the mass, the weight of the companion of the star. But what are we talking about? What is this variation? Well, the variation is extremely little. So if we were outside the solar and we will be looking at the sun with a spectrograph, we will see Jupiter produces a variation in the sun's velocity of 30 per second, and the Earth only 9 centimeters per second. So you can imagine this is a tiny little variation in the position of the lines that are very hard to detect. And when can we see it better? The brighter the star is and the more massive the planet is, the better the detection of these lines. So basically, this method, what allows me to know is what is the mass of the planet that is orbiting around the star, but we don't know how big this planet is. Then it comes a second method to be able to indirectly detect planets, and it's called the transit photometry. And I think this is much easier to understand what's going on. So imagine that you are observing a star, and between you and the star, you can see a planet passing in front of the disk of the star. It's what happens in an eclipse, or you have heard probably about the transit of Venus. So when we are looking with a telescope and we are counting the photons that are coming from the star, we can see that when the planet is passing in front of the star, we receive less light from the star. And that, if I do a plot of number of photons versus, means that I see how the light goes down. And this is a light deep in the light curve is the transit. So, of course, depending on the size of the planet, or better said, depending on the relation between the size of the planet and the size of the star, the dip in the light curve will be different. So the bigger the planet, like in the case of Jupiter, for example, the more it will change the light that we receive from the star. So you can see in this plot here, if our planet is like Jupiter, it produces a variation in the light curve of 1%. But if it's as little as the Earth, it produces a variation of 0.01%. So again, this little variation is much more difficult to detect. The way of measuring, of hunting, let's say, for smaller planets would be, okay, what happens if we look at stars that are smaller? So smaller planets, because the ratio between their surfaces is bigger. And indeed, that's the case. So sometimes it's better to look at the smaller stars to detect the smaller planets. But again, this technique allows us to know only another parameter related to the planet, that is the size, its radius. And this, it says nothing about the mass or the weight. So I have presented 3 methods for detecting exoplanets, which are very good. Now the question is, where are these planets? Because the stars don't come with saying, I host a planet. So we have to do surveys. That means we have to explore the sky, we have to monitor a lot of stars and see when we see a variation in the stars. And for that, there are ground surveys. So I put here some pictures of different telescopes that are conducting surveys in radial velocity, so with the spectroscopic technique, or transit surveys by trying to measure the variation in the light curve. So telescopes are just pointing towards certain directions in the sky for long time enough to see where they detect these variations. And this is how we detect the planets that we know. But of course, in the ground, there are amazing things that can be done, but we have a problem that is the atmosphere. The atmosphere brings turbulence, makes this not so nice to analyze. So if we don't want to have the atmosphere perturbing us, we have to go to space. So there have been surveys from space, actually space telescopes designed only to search for planets. And all of them, they use the transit technique. The first one was the French Keop that worked between 2007 and 2012 and discovered 30 exoplanets. Very close to the launch date of Keop, 2 years later, the American satellite Kepler launched. It was observing at a certain region of the sky here for several years. It produced discovery of exoplanets. So most of these forces are coming from the work done by Kepler. After some years of staring at the Cygnus field, the reaction wheels of Kepler, two of them were not working anymore, and it couldn't point to that region. So they found that the stable pointing was around the ecliptic, and then the second version of Kepler, Kepler 2, that is the same telescope but pointing in a different direction, came, and it produced a lot of more discoveries for 4 or 5 years. So Kepler stopped working a couple of years ago because its fuel ran out. But in 2018, the American mission TESS was launched, and TESS is currently serving the whole sky of the whole sky. So looking for variations in the stars, particularly bright stars. And so far, we know 91 more planets thanks to this. So here are the different techniques that are used to detecting extrasolar planets. As you can see, the one that has brought most of the known exoplanets is the transit technique, basically through its surface sky. Then we have the radial velocity and some 150 direct imaging. And this is a field, the exoplanet field, that is changing constantly. Today, if one has to make a presentation, has to update the numbers, checking how many planets do we know. So this infographics was made by ESA in 2019, so a little bit more than 1 year ago. Numbers don't hold anymore. I didn't update all the numbers, but basically every now and then there is a new planet discovered. So it's really a very dynamic field where everything is changing day by day. Okay, so we have, although we are still discovering a lot, we have to give a step further and not only discover planets, but also be able to do a good characterization. So to try to understand how these planets form, what are these planets made of, how are planetary systems evolving. So we need to be able to measure more precisely some parameters. And this is the next step, is saying, okay, let's combine results coming from different observations. So we are entering the year of characterizing extrasolar planets. And as I mentioned before, from the two most successful techniques of indirect detections, the transit and the radial velocity measurements, we can get two crucial parameters. So the mass from the radial velocity measurement and the radius or the size from the transit. And if we consider this to be a perfect sphere, it's very easy to obtain what is the mean density. So having an insight of what these planets are made of. And how do we do that? Well, we know we can construct models. We know that different materials have different densities, and so start to make spheres of a certain material and of a certain size. I can know what is the mass contained. So basically, this is what people trying to understand what planets are made of are doing. So they construct diagrams like this of spheres made of different compositions. And when we measure the mass and the planet, the mass and the radius of a planet, we place the measurement in this diagram, and we can have an idea whether this planet is rocky like the Earth or is more gaseous and it's going above here. So if the density is very low, it might be composed by hydrogen and helium. Or if the planet is very dense, it might be almost iron. And this allows us to know whether we can search for habitable planets, because we don't know life living in a gaseous atmosphere, but what we know is life where water is, where a solid surface is. So these are the kinds of things we are trying to understand. So just to summarize a little bit from here, this is sort of a detective work. And if I'm going to do a parabola of, well, let's imagine that we get a picture of the shadow of a person. And by knowing when the picture was obtained, where the sun was, what day it was, we can know how high this person is, what is the length of their legs or of their arms. And then if another person tells me, okay, but I have seen these footprints and I know how much the snow has come, then I can know how much the person weighs. So now if I combine the two and add to this a model of the human body and how the mass is distributed in the human body and how the fat is distributed, then I can know probably if that person was a man or a woman. I may not be able to know if the person was had red hair, was blonde, or it has blue eyes, but I know some basics of what is the subject I'm looking at. So this is the kind of work we are trying to do with planets. So if we know the mass and the size, what we are trying to know is what they are made of. Are they made of rocky composition like the Earth? Are they ice giants like Uranus and Neptune? Are gas giants like Jupiter? Or are they something that we don't know from the solar system? That is what conforms this continuous and this zoo of planets that we are now allowed to know because we observe the exoplanets. And so here is where CHEOPS comes into the play. So the idea is to characterize exoplanets. So CHEOPS is a jointly Swiss and ESA led satellite. It is the first ESA small mission, and the CHEOPS consortium is composed by Switzerland and 10 European countries that are marked here, where Switzerland is leading the consortium. A small mission means that it has to be done fast and with a limited budget, more or less limited to 100 million euros. So doing something fast and with little budget means it cannot be very big. It doesn't mean that it cannot do great science. So CHEOPS is a reflector telescope of 30 centimeters. So the diameter of the mirror is 30 centimeters, so it's not very big. But it can, or the idea of the line was to perform high accuracy transit photometry on single targets. What does it mean? CHEOPS doesn't do a survey. It's not doing what TESS or Kepler or Corot did. It's pointing toward planets, towards stars, where we know there are and where we want to improve knowledge of these planets. So CHEOPS is putting quality over quantity, high precision photometry on relatively small sample of well-selected targets. But for doing that, we need flexibility to look where an interesting target is. And so we need to access as much of the sky as possible. So another design jobs was to access the whole sky. The whole sky is not possible for thermal reasons, but CHEOPS can access 70% of the sky, excluding the ecliptic poles, which is already pretty good. And then to really bring something to the table, CHEOPS has to do exquisite photometry with very high precision. And so one of the requirements of the mission was to be able to detect a planet of the size of Earth going around a star like the sun with what we call a signal to noise ratio better than 5. And what do we mean by this? Well, a planet like the Earth, if we go outside the solar system and we see transiting in front of the sun, will make a variation in the light curve of 100 parsecs, so 0.01%. And we want to be able to measure that with an error lower than 20 parts per million. So basically what you see in this plot, we want the error bars to be as little as this in a transit depth of 100 ppm. So let's stop a little bit with the science and let's see how this mission was developed in time. So in 2012, there was a call by ESA to select the small mission. And there, Switzerland, together with other European countries, presented this proposal that was selected among many others. So there we started working in the design of the mission. So here we see the design of the instrument, the telescope, with the electronics. Here is the mirror and the secondary mirror, and the platform. So where the instrument is mounted, the satellite that has inside the onboard computer, the power supply, the reaction wheels, etc. So after the completion of the design, the construction phase started. The different components of the instrument were provided, but the different members of the consortium, they were sent to Switzerland to Bern, and they were assembled here at the university. And after we assembled the telescope was sent to Madrid to be integrated in spacecraft. And then it did the tour around Europe to do several final system tests, and the satellite was completed and ready for launch in 2019. We waited 6 months until we launched on the 18th November of 2019. And because we are still close to the date of launch, I would like to share with you how this very nice and moving moment happened. So I have a little video that shows the launch of CHEOPS from French Guyana.
She does so par la station du Canada pour passengers to be launched. During the break via the internet, we're watching it on the screen. So very cool. The VIPs and visitors. For the second part of the broadcast, we're moving in at plus 2 hours and 1 minute. So enjoy the break. We'll see you back
centrale qui assure cette poussée pour s'arracher à l'attraction.
So here you can see part of the Keops team that attended the launch in Kourou. A lot of happy people celebrating after 2 hours after the launch, when we knew that Keops was successfully injected in its orbit. And where is Keops? Where is Keops orbit? So Keops is going around the at kilometers from the Earth's surface in a polar orbit. And it's a special orbit because Keops is going to Earth in what we call the day-night termination, meaning the place where the division between day and night happens. So the sun is towards our left, and the deep sky is, sorry, the other way around, is towards the right, and the sky is towards the left. And every time Keops flies over Madrid, it sends the data that it has taken. And in Madrid, we have the antennas that receive the data that then are transferred to Geneva, to the Science Operations Center, where the data is processed and then sent to the scientists that are going to do the analysis of this data. So what happened after the launch? Well, after the launch, the in-orbit commissioning started. So actually after the launch, we had some holidays, a Christmas break, and on January, we started the in-orbit commissioning in Madrid. Around 20 days later, we opened the cover. So the telescope is launched with a cover to prevent it from getting dirt during the launch. And of course, if the cover doesn't open, we cannot see anything, but luckily everything went perfect. And we were able to see the first star, the first light. And here is how a star looks like in the focal plane of the telescope. So you might be surprised to see this triangular shape. This is the focus image of the star. And if we were to look at this star from the ground, we will see this as circular, but it turns out that the is held by 3 points. And due to the change in temperature from the room temperature on the Earth to the temperature in space, the mirror suffers from the stress of being attached by these 3 places, and it deforms, giving this triangular shape. So we knew this was going to happen. It was no surprise. Actually, we were shape just as we of course, as I mentioned before, we cannot see the planet. So this is not the planet, this is the star, and these are the background stars. And what we are doing is to measure the light coming from the star. So the commissioning went very well. We were very lucky because the pandemic was stopped, but we were able to do all that we needed to end the commissioning. And actually, we ended the commissioning already in home office on the 25th of March. And in mid-April, we started the routine operations. So we've been operating, doing the nominal science for the last around 8 to 10 months. Talking about science, let's say what CHEOPS does. But let me first remind again what CHEOPS is supposed to do. So as we said before, we are not a discovery mission. The idea is that we go to search, to look at planets that we already know. And what we want is to improve measurements. And then we want to combine our measurements with observations done on the ground, with radial velocity observations that provide us the mass, and to combine the two to be able to characterize the planets and to know whether these are rocky worlds or gas planets or water world or ice planets. So please keep this in mind. So what are the science cases that CHEOPS studies? Well, first of all, we have to distinguish that there are 2 programs. 80% of the time is assigned to the warranted time observing program. That means it's time given to the CHEOPS consortium, so to all the member states that have contributed to this mission. And so the CHEOPS consortium decided to organize the science objectives in 6 programs. The first one is actually to do what I've been mentioning, to improve the size measurements of the planet by measuring the transits with very high precision, and to combine them with radial velocity measurements to be able to characterize the composition of these planets, and also to put constraints on the formation scenarios that were behind these planets. But this is not the only thing that we are interested in. It's also another of the topics of CHEOPS to say, okay, let's assume that we have the measurements, the radial velocity measurements of some planets, but we don't know if the planet is transiting or not. So with the radial measurements, if the planet is transiting, we can know when that event should occur. We can point CHEOPS towards the star and see whether we see a transit or not. this is a let's say, high risk observation, because it might be that you are sort of wasting time, but you can also learn a lot about the star itself when you are observing this. The third scientific topic is to characterize the atmosphere of the planets. So when we observe the planet, not only when it's transiting, but when it's going all around the star, we can see how the light curve is changing due to the refract from the star. And this allows us to learn things about the planet atmosphere. And I will come back to this later when we see what are the results already produced by CHEOPS. Another interesting topic that can be done with CHEOPS due to its very precise photometry is to actually be able to see if there are other features that can be detected. For example, rings or moons or the formations in the planets. As CHEOPS is looking, let's say, the of a planet, we can try to see if this shadow is different from what we would expect from a perfectly spherical planet, or for a planet that has no moon around or no ring around it. And this is very interesting because in all these more than 4,000 planets that we know, we don't know any planet that has a ring or a moon. One of the last topics is to search for new planets. And as I mentioned before, CHEOPS is not a discovery mission. So it's not that we are pointing around just to see what we can detect. But when we observe a planetary system, so systems where there is more than one planet orbiting around the star, there is a great chance that there are more planets. So CHEOPS is trying to see if there are more planets where we already know that there are some planets. And we will see also the consequences of that in a minute. And finally, because all these missions usually have to be scheduled at very specific times, there are, let's say, gaps of time between observation and observation where, let's say, we don't have anything to observe, but we don't waste the time. We observe at other stars, and we do the ancillary science. We are trying to characterize stars that then will allow us to understand better what happens when these stars have a planet. 80% of the time is allocated to the community. So people, astronomers that don't belong to the CHEOPS consortium can use the CHEOPS telescope by making a proposal to ESA, saying what they want to do. And then if they have a good idea, then time is granted for them. And this is done through calls every year that I will mention later. Okay, so now the juicy part. What are the CHEOPS first results? So since we started nominal operations in April last, there have been a lot of results, very interesting ones, some of which have already been published that are now in the pipeline of the paper production. So we have 4 papers that we can talk about because they are published, and that I will present their main results in this talk. So one is presenting the CHEOPS mission and what is the performance that can be achieved with CHEOPS. Another one is about how can we characterize some features of the atmosphere of a hot Jupiter. A third one that is a planetary system of 6 planets. This is a paper that will be in a press release on the 25th of January. So what I'm going to say stays between us. So this cannot be released to the media yet, but it's an extremely interesting result. And it's worth mentioning it in some detail. And finally, another planetary system that was discovered by TESS, and where refinement on the measurements were done. So let's start with the first paper, the CHEOPS mission. So here this paper is basically presenting community, say CHEOPS was to do, what are its capabilities, and to illustrate what CHEOPS is able to do, we publish the results obtained during commissioning. And so during commissioning, we wanted to know if CHEOPS was able to perform as well as it was designed for. And remember that I said that we wanted to be able to detect the signal of an Earth-like planet around the sun with a signal to noise ratio of 5, or with an uncertainty of 20 parts per million. So we observed a star that is a magnitude 9 star. So in the magnitude range of CHEOPS, that very bright stars are magnitude 6 and very faint stars are magnitude 12. This is in the middle, more or less. We observed a solar-like star. We knew that there was not here, and we wanted to know what is the precision, or to what level can we say that actually there is no planet. And what we obtained was that the precision that could be achieved 15.5 parts per million. So in this case, we were aiming at 20, and we did better. We did 15.5. So this is actually great. It gives us a lot of confidence. And then in the later results, that really, especially for the brighter stars, the precision obtained with CHEOPS is amazing. But then, of course, we wanted to measure transit. So we observed a well-known hot Jupiter, one of the planets of the Kepler-11 system. So this is a hot Jupiter that has a size of around 1.37 radius of Jupiter. And wanted to see if we recover actually from our transit measurements what we knew. Well, we recover the measurement, so we actually measure 1.29.5 Jupiter radii, but with a precision 5 times better than in the discovery paper. So only one CHEOPS transit already improved the knowledge and the precision of this radius by a factor of 5. So the error by which the radius of these planets was determined reduced by a factor. This is really great. And you can see the light curve here. So this is the way CHEOPS was introduced to the astronomical community. But of course, become much more interesting when you present original results, things that nobody knew before. And here is the first scientific paper of CHEOPS, that is the hot day-side and asymmetric transits of WASP 189b as seen by CHEOPS. So let's start by saying which is the star that we observed. So we observed a star that it's bigger and hotter than the sun. It's a very bright star. It's magnitude 6.6. So if you have very good eyes, you might be able to see it. So it's in the limit of the human detection, which means very bright for a telescope. We knew that this star has one planet that rotates around the star in less than 3 days, and that the mass of this planet is around 2 times the mass of Jupiter. And it was discovered in 2018. So the idea of this was to know better, let's say, this planet. And very interesting results were found by analyzing two things. So we have the planet, we measure the transit when the planet goes in front of the star, but we can also look what happens when the planet is hidden by the star. And these were the two moments when this star was observed. But let's start first with the transit. This is what we've been talking about. So this is the light curve obtained with the measurements done by Keops. The red line that is, let's say, fitting the data that are the blue and the black points. And actually there is also a green line here. I don't know if you can see it, that is a bit shifted from the red. So the first result is, let's say, the easy one, is to measure how deep the dip in the light curve is. And here it came the first surprise. The planet was bigger than previously measured. So the Keops photometry is such that allowed us to determine the radius of the planet much better than it was known before. It turns out that this planet has a radius that is 15% larger than originally measured. But also, when we go into the details, we see that the light curve is not the light curve, the transit is not symmetric, and this is the difference between the red and the green lines that are fitted here. So what we see here is what we call the residuals. So basically subtracting the data points, so the points here, to the two lines fitted. And as you can see, the green one has some structure, but the red one is completely flat, meaning that this case is the one that is best approximating the transit. And this is the case of an asymmetric transit. And what does it mean that the transit is asymmetric? Well, it turns out that this star is a fast rotator. So it's really spinning around its own axis at a very fast rate. This makes the star not to be a perfect sphere, but to be like a baseball ball. So flat in the poles and large in the equator. And this produces what is called gravity darkening. So it means that it's brighter in the poles and darker in the equator. And the fact that the star is darker in the equator is what makes this asymmetric transit appear here. Moreover, as you can see, the brighter part is this one. So here is the pole of the star and here is the equator. So the planet is going into a very obliquity, into a highly inclined orbit, sorry. So it's not like the planets of the solar system going around the star in the plane, but going in the plane of the poles. Okay, but then it comes the second interesting point, that is looking at what happens when the planet goes behind the star. So we know that when it goes in front, we measure the transit, but then in all the way around, the planet is reflecting the light from the star. And how much it reflects, it will depend on how much of the surface of the planet is illuminated. So this is what is called the phase curve. So what we measure in all this trajectory is the combined light of the star plus what is reflected on the planet's surface. But when the planet is behind the star, we only measure the light from the star, meaning that if we have that from the other parts, about how much is reflected from the planet. And this is what is measured here. So this is the occultation. So it's the dip when the planet goes on the behind, but just to know what happens in the atmosphere. And it allows to determine that the temperature of the atmosphere is 3,200 Kelvin. So extremely hot. So this is for the first scientific paper. The precision to which this was measured is only less than 5 parts per million. So much better than was originally foreseen as the precision of CHEOPS. So let's go to the second paper, scientific paper that presents scientific results. So this is the paper I mentioned, it's embargo until next Monday. So yes, no media of what I'm going to show. And it's about a planetary system that has 6 transiting planets in what we call a chain of Laplace resonances. So the picture here doesn't depict this planetary system, TOI 178. It depicts a Kepler 11 system. So remember Kepler 11b, we measure it during commissioning, but it sort of also illustrates a little bit the situation of the system, although here there are no resonances. So that makes TOI 178 much more interesting. But let's know a little bit of the that is not so old. TOI 178 was first observed by the TESS satellite during 26 days in August and September of 2018. And then it was already proposed that there were 3 planets orbiting this star, one with 6.55 days, 996, and another at 1035 days. There were follow-up observations, several ground telescopes, and where the first 2 planets were confirmed, there was something going on with the third one, that sometimes that transit was detected, sometimes not, so something weird was going on. So in August last year, Keops observed during 11 days this system, confirmed the planets at 6.55 days and 9.96 days, but also discovered 2 more planets that were inside this orbit, so orbiting only at 1.9 and 3.2 days. But again, it didn't detect the planet at 1035 days. So what's going on here? With Keops, we knew that there were 4 planets. And when looking at the periods of these planets, you see that when the planet C does 2 orbits around the star, the planet D does 1. When the planet D does 3 orbits around the star, the planet E does 2. And this is what in astrophysics we call mean resonances. So when go around the star in commensurable times, they are in mean motion resonances. And this is very important. These are the Rosetta Stones of the planetary systems, and I will tell you later why. So when analyzing all the data again, this idea that maybe there was a planet at twice the period of this 10.35, so at 20.7. And also there seemed to be another weird thing happening on the planet. So astronomers, theoreticians said, okay, let's see, if there is a planet with a period of 20.7 days, when is the going to happen? They calculated the date, the time, and voila, the planet was there. So this was really a great result also for doing theoretical astronomy, to be able to predict an event and this event happened. So great, so we added a new one, so a 5th planet. But then, as I mentioned before, there was evidence of another planet. And following this reasoning of the resonances, I mean, just because nature likes these kinds of things, the 6th planet was supposed to have a period of 13.4 or 15.5 days. And so again, theoreticians did the calculation when the transit should happen, and planet F confirmed with a period of 15.23 days. So these planets, these 6 planets, so starting with the test measurements of 2 planets, ending with CHEOPS, with 6 planets, and all these planets in mean motion resonances is an extreme. So here you can see the light curves, the first one of the 11 days of observation, and the 2 then later to discover the planet F and G. These planets were also confirmed by follow-up observations from the ground, and their masses were obtained doing radial velocity measurements. So you can see here the list of all the planets with their masses and their periods. And it happens that except from for the first one, the other 5, and it was called a Laplace resonant chain. And what does it mean? It means that planet C, in these 2, 9, 12, planet C goes around the star 12 times when the planet She does it 2 times. And the planet D does the same, but 9 times when the planet She does it 2 times, and the X times, and the F 4 times. These planets, because we have the mass and the radius, we can estimate what their composition is. And the first 2 are what's called super Earths, so they are very likely rocky planets, and the other 4 are mini Neptunes, so planets with a more gaseous composition. So this change of planets in mean motion resonances are the Rosetta Stones of the formation of planetary systems, as I mentioned before, because this is very important for formation theories, that when you do models, you see that planetary systems come out in mean motion resonances, but sometimes it's very difficult to find this in nature because many events may happen after the formation. So really having these kinds of systems that we have only a handful of them is very important to confront with the theory. And finally, and very quickly, the last result, it's again a system where a fit was discovered by Keops, and with a lot of improvement in the planetary sizes and masses. So also very new history. Early in 2020, again, the Space Telescope test discovered a planetary system with 4 planets orbiting around the solar plexus. And here, this picture depicts how it looked like. And the idea of the observations was to improve the knowledge that we have in particular, so basically knowing when the transits are going to happen. And just by chance, when looking at light curves, another planet was there. So basically, in the 3rd Keops observation, after the transit planet B, the planet F was found. So here we have the measured radius and masses. There are only a few radial velocity measurements, so the masses are not well constrained. Some are only coming from models, but it's to have an idea what are we talking about. So it's again super Earths and mini Neptunes. So we can say that Keops has added a new planet to the family member with an orbital period of around 30 days. So with this, I finish with this of Keops. Mention lastly the Keops guest observance program, that is this 20% of time allocated for people that are not part of the Keops consortium. There are announcements every year, so please be aware of this. So there were 12 observing programs accepted during year 1. And the second call was closed in December last year, and it's being evaluated right now. We have to start with the observations in March. So with this, I want to finalize. I hope you're convinced that CHEOPS is doing great science. Please stay tuned because there is a lot more to come. And yes, 1 year in space and going strong. Thank you.
Thank you very much, Andrea, for this very interesting talk and these insights into the CHEOPS mission. So we would now come to the question session. So please write into the chat or raise your hand, and we can then unmute you and if you have a question. Okay, we have a first question by Aaron Bonnet. You need to still, yes, unmute. Thank you.
Thank you very much. Congratulations for this excellent presentation of CHEOPS. I am very interested in the results, of course, and this is remarkable. It's a small mission, but when you build a mission, the word small means also that it is cheap. Do you know how much it costed to the Swiss people and to the European people? How much was the total cost of CHEOPS, and how much did Switzerland contribute to it?
Yes, so the total cost of the mission is around between 100 and 110 million euros. This accounts for the build of the mission, also of the instrument, the launch, and also the 3.5 years of work since launch. So from this, 50 million was covered by ESA, mostly a big deal of it is the launch itself. It's also paying for the Mission Operations Center in Madrid, or partly of this, and also it provides the CCD, the camera for the mission. Then from the CHEOPS consortium, so we have around 50 or 60 million more. Switzerland has a share of 30%. So yeah, you can think more or less around 30 something million euros.
Thank you very much. An excellent answer. Thank you. An excellent mission. Congratulations.
There are more questions. I'm sure there are more questions. Yes, now we have many. Maybe we first take Jochen Eislöffel, please. You need to unmute your microphone for before you can speak. Otherwise, we cannot hear you. It is in the bottom left of the Zoom screen. You can there where it says mute. Or if you prefer, you can also type into the chat if you want. Yes, we know that we have to unmute, but it's unmuted. It's but we cannot unmute on the participant side. Yes, okay. Maybe we wait and we will go first for the question by Sushin Yoshi.
Hi, can you?
We could hear you, but now you're gone.
now he's back.
Yes, now it's good.
How is it now? Okay, so I had these questions like, as Andrea told, CHEOPS is mainly targeting the stars which we already know that they have the planets. But there are a lot of stars like that we know that they have the planetary systems that we have detected. But how the CHEOPS science community decides what stars to target and what are the main parameters to prioritize them?
Yes, that's the task exactly of the science team of Keop. So, so let me tell you how the science team is composed. So we have these 10 countries program that are part of the consortium. And this means that they have representatives in what we call the science team. And the science team is the one that is in charge to define the kind of science that we want to do with Keops. The group of people that have defined the different programs that I have shown. So these people that are scientists and are working exoplanet data all the time, based on these programs, select which are the most interested to carry on the science that they want to do. So taking measurements from ground observations, from other space observations, the target stars are selected. So for example, in the last two papers that I mentioned, the targets came from the TESS telescope. And this is a very interesting thing because it's part of a synergy that has been enabled between the two. So this is, as I mentioned, a satellite that is the whole sky, but it's composed by 4 telescopes, but each telescope is only 10 centimeters in size. This clearly, I mean, there's something that is very difficult or impossible to convince, that is the size of the mirror. The larger the mirror is, the more light you can collect, and therefore the more precise you can. So you cannot ask TESS to be able to do that was a satellite of almost 1 meter. So they are great at discovering planets, but then to have a better knowledge, it's better to go with a larger telescope and extract more. And so there is, for example, a collaboration with TESS in detecting what are the most interesting targets to be observed then by Keop. So in that sense, it's really great. Satellites are working in parallel because it's almost like immediately after a discovery, we can point and look at the star. This has a lot of advantages in terms of prediction of when a transit is going to happen. And as you have seen, the two cases that we have analyzed are systems that were discovered in the last 2 years. So this is due to this great interaction that happens between the two. And basically the targets are selected because people are in the exoplanet field, in the exoplanet community, and they know which are the most interesting to look at.
Okay, thanks a lot.
The next question is by Matthias Beck. Please, Matthias.
Yes, hello. So I will not ask a question about CHEOPS, Andrea, because we have been doing CHEOPS together. But I will ask a question that is maybe even more difficult for you to answer. So looking ahead, so CHEOPS is a lifetime of 3.5 years, and then possibly an extension of 1.5 years. So from your perspective, what could be an interesting and sort of challenging follow-on project for the exoplanet domain and for Switzerland?
We were joking that he was not supposed to make questions. So okay, I think we have aimed big. Now we have done the small. We have to go for the big ones. This project that is really in the very starting life. and it's very ambitious. It's trying to actually be able to do direct imaging of planets. And yeah, I think that's the way to go. I think has proven to be able to do a mission as a one. It's been great the way everything was done. So I think Switzerland is ready to do something bigger, and I think that the is a really the next thing to do. We need to know also more planets are formed. We need to put more constraints to planetary models. So we need to have direct imaging. Yes.
Okay, thank you very much. So let's go to live.
Is there another question? Maybe I can also ask one. I mean, what I saw is that this mission of preparing the satellite, getting ready, this was really a very intense thing. There's a lot of emotions also. What was for you personally, maybe say the best, and what was the worst moment in this very intense journey?
They happen one day after the other.
Oh.
So the launch was planned on the 17th of December. And we went there, and less than 2 hours before the launch was canceled. And it was canceled for us for an unknown reason. They are very hermetic in what they tell you. And believe me, when you hear it's canceled and you don't know why, and you don't know how, you feel that the whole world comes and falls down, and it's, when is it going? Next week, in 1 month, in 1 year? When? We were very lucky because it was the next day. And then it's when the happiest moment came. Knowing 2 hours after the launch that Keops was in the right order, that everything was a success. And then, well, during commissioning, there were many moments. Of course, cover, seeing the first light was something that was very important. Seeing that everything was acted was, and the unexpected things were a bit worrying, but luckily we didn't have too much of them, or not for too long. So I think, yes, the happiest and the most terrifying moment came very close together. Luckily, first the bad one, and then the good.
Thank you. Yeah, I can believe that. Are there more questions? I see it's already 19 hours 35, so we are already advanced. If then there is no further question, I would of course first like to thank Andrea Fortier very much for joining us tonight. Thank you very much. I also thank everybody who has connected. But before we disconnect, let me also give a quick outlook. So in March, for the next activities of ProESI, we have planned a talk of our former president, Professor Adrian Yaki. And then in May, we are planning to have something new, which a format which we didn't do before, namely that instead of having one long talk, having 2 shorter talks by the postdocs working at EC, to connect also a little bit ProEC, a little bit more to EC itself. This is also an idea from our side to compensate a bit for the fact that during 2020 we did not have as many activities as usual in ProEC, and we would like to compensate that a little bit with this extra talk. And then later in October, we will return to the normal talks, and who knows, maybe by then, or maybe even for earlier, I don't know, we will have the possibility to meet again. With that, I thank you very much again for joining, and I wish everybody a very nice evening. And thank you, Andrea. Bye-bye.
Thank you.